looking at trigonometric functions of angles in standard position. And we'll just start by taking an example of a right triangle. And we want to be able to find the sine of angle A. So let's just do a little review from grade 10. Can you label the opposite, adjacent, and hypotenuse? And we'll write the definitions for sine, cosine, and tangent. You remember the trick for remembering sine, cosine, and tan, right? So we'll use SOHCAHTOA to help remember the angles, or the ratios. The easiest side to put on the triangle is the longest side, aka the hypotenuse. And I'm just going to shorten that as hype. The opposite side is the side that is exactly opposite to the angle. So it's not touching the angle in any way. This line here does not touch angle A at all. Okay. And the adjacent side is the side, adjacent means right beside. The adjacent side does touch that angle A. Okay, so the SO in SOHCAHTOA means that sine of the angle is opposite over hypotenuse. Okay, so sine is just a ratio of sides. The cosine of an angle is adjacent over hypotenuse. And the tangent of an angle is opposite over adjacent. And did you learn about cosecant and secant? No? Okay, wonderful. We do have some new things to learn. That'll come up later this week, next week. So now just imagine that I'm going to keep the base of the triangle fixed. I'm going to keep this line the same. And I'm just going to take the opposite side and I'm going to make it bigger. Whee! And that'll make a new triangle. Okay, so I'm looking at this right triangle now that's around everything. So when I make that angle A bigger, what happens to the sine? It gets bigger. The opposite side gets bigger. And the hypotenuse gets a little bit bigger. So both of them are getting bigger at the same time. So as I increase the size of the opposite side of the triangle, as I change the angle A and make angle A bigger, then the opposite side of the triangle gets bigger. So now imagine that I keep doing this. So I'm going to keep increasing A. Okay, and I'm going to make that angle A bigger and bigger and bigger and bigger until that angle becomes 90 degrees. How does the opposite side compare with the length of the hypotenuse? It's getting close to the same. And the bigger that I make angle A, opposite side is getting big really fast, but the hypotenuse doesn't get that much bigger. Okay. So the opposite side gets close to the same as the hypotenuse. So what happens to the value of sine A as A increases from 0 to an angle close to 90? Yeah. So if I start with an angle of 0 degrees, really close to 0, this sort of triangle, do you know what the sine of that triangle is? Really, 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 really small. So when you have a really, really, really small triangle, then the sine of that is going to be almost 0. Because it's a really, 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 really small number, like 0.0001 over 2. That's going to be really close to 0, just as an example. Okay, I'm making a really, really small triangle. Sine is going to be pretty much 0. Now if I make the opposite side really big, close to 90 degrees, so just a little bit less than 90. What's going to happen is I make this angle bigger and bigger. The sine is going to become almost 1, because the opposite side and the hypotenuse are going to be almost the same length. When it's exactly 90, you can think of it as being like an infinite equilateral triangle, where the top point is at infinity. Then the opposite side and the hypotenuse will be the same. So when the angle is 90 degrees, it's like an infinite isosceles. Okay, but really it doesn't make a triangle even. Those two lines, the opposite and the hypotenuse, will never really meet. They kind of meet at infinity. The opposite side will equal the hypotenuse. So what's the value of sine 90? Exactly 1. If the opposite and the hypotenuse are the same, then opposite divided by hypotenuse is 1. And if we plot angles on the unit circle, this will help us to figure out trigonometric functions for angles that are bigger than 90, where we can't make a triangle. Now, a really cool and useful fact is that if you're on a unit circle, then cosine is the same as the x-coordinate, and sine is the same as the y-coordinate on a unit circle. Okay, a unit circle just means that the radius is 1. So let's prove this fact. So do you know what letter we can call this length here? X. It's on the x-axis. So this length is x. I know I'm asking very easy questions. And this length here, y. And this length here, trick question. It's the radius, right? It goes from the center to the outside. So this is r. But I'm saying that this is a unit circle. So by the definition of a unit circle, radius is 1. So if I want to find sine theta, I'm going to use my rules from the top of the page. SOHCAHTOA tells me that sine is opposite over hypotenuse. Here's my angle, the standard position angle. Standard position always starts from the x-axis and then goes around counterclockwise. So the standard position sine, the sine of the standard position angle is opposite side over hypotenuse. What's the opposite side? Y. And the hypotenuse? 1. So sine is the y-coordinate. And that works for anywhere on the unit circle. It doesn't even matter if I can make a triangle there or not. So if I'm over here, then I can find the sine of this angle just by looking at the y-coordinate at this point. It's quite amazing. The cosine is adjacent over hypotenuse. The adjacent side is x, and my hypotenuse is 1 because the radius is 1. So the cosine is x. And this works on any unit circle. So it also works for points over here where I can't make a triangle. And we'll see that on the next page. So I think that you've learned these trigonometric ratios last year in degrees, and we're going to do them in radians. Okay, so an angle of 0 in standard position is just a line on the x-axis. And we can't make a triangle with that, so we can't analyze it using sine as opposite over hypotenuse. But we can use the fact that we just proved on the last page. To find the sine of that angle, all we need to know is the coordinates. Now on all of these circles, the radius is 1. These are all unit circles. So do you know what the x-coordinate is at that point? It's 1, because I'm 1 away from the origin. And how high am I? So I'm not high at all, I'm 0. Okay, so the x-coordinate gives me cosine. The y-coordinate gives me sine. So sine of 0 is 0. Cosine of 0 is 1. How beautiful. Yeah, this is very handy. If you have an angle of pi over 2, do you remember how many quadrants that is? This is 1 quadrant. Pi over 2 is the same as 1 quadrant. That's the same as 90 degrees. So if your angle is 90 degrees, again, I can't make a triangle there. Okay, anytime you're making a triangle, you're always trying to make it with the x-axis. This would be like an infinite triangle that we talked about at the beginning. Sine of pi over 2 is the x-coordinate at that point. Or, sorry, the y-coordinate. So do you know what the y-coordinate is? I'm up 1 and over 0. So my y gives me my sine value. Sine of 90 is 1. Or sine of pi over 2. So that's the same as sine of 90 degrees. Cosine of 90 is 0. Okay. Pi is the same as 2 pi's over 2. So that means 2 quadrants. So 1 quadrant, 2 quadrants. It's the same as 180 degrees. So no way I can make a triangle there, but I can still find sine and cosine. So how high am I? I have a y-coordinate of 0. I'm not above the y-axis at all. And my x-coordinate is now on the left-hand side. My x-coordinate is negative. So sine of pi is the y part, 0. Cos of pi is negative 1. And that's the same as sine of 180 degrees and cosine of 180 degrees. Okay, so you try the last two. See if you can figure out what the sine and cosine is for those values. And it's possible to verify this with a graphing calculator. You just make sure that you're in the right mode, radi in this case, and then you can find sine of pi and cosine of pi. Okay, good job everyone. 3 pi over 2 is the same as 3 quadrants, because each time you go over 2, you're going over through one quadrant, 90 degrees. So we got 1, 2, 3 quadrants. Draw the angle there. The y-coordinate is negative, and the x-coordinate is 0. So that means that the sine is negative, and the cosine is 0. 2 pi is the same as 0. So I can just copy my answers from the first box. And you could imagine that you could keep going around and around like this in circles forever. The next one will be 5 pi over 2 and then 6 pi over 2. These patterns start to repeat. So sine goes 0, 1, 0, negative 1, 0, 1, 0, negative 1, and on and on and on. Now what about tangent? Let's check that on the calculator. Tangent of 0. Tan of 0 is 0. Tan of pi over 2 is domain error. So we can write infinity or does not exist. Tan of pi is 0. Can you guess what tan of 3 pi over 2 might be? 3 pi over 2 does not exist, domain error. And can you see a pattern? 2 pi will be 0 again. So 10 goes 0, does not exist, 0, does not exist, 0. So the question is, what's going to happen to the sine and cosine ratios if we keep going? If I made another row on this table, what would the next row be? First sine. Sine, what if I did 5 pi over 2? The next one. I would get 1, 0, infinity, does not exist. They start to repeat. Okay, sine and cosine repeat every 360 degrees. So after 2 pi, they'll start to have the same angles again, the same ratios. How long does it take for tangent to repeat? Only every 2 terms it repeats. So that's every 180 degrees. So after 180 degrees, tangent repeats. Which is pi radians. And can you find any way to determine the tangent just by using the sine and cosine? So is there a way that we can get these answers using just sine and cosine? Zero divided by 1 is 0. 1 divided by 0 is infinity. Maybe if we divide the sine and cosine, maybe that gives us tangent. That seems like a pretty good guess based on the table. Let's check it using some numbers. So let's try with some other values and see if Brody's hypothesis will work. You guys are going to have YouTube fame after this video goes viral. So I just did cosine 215 and I got 0.1977, which is totally wrong. Anybody know why? I'm in radian mode. So I know what my answer should be. I've got to make sure that if I'm doing something in degrees, I go in degrees because the answer is totally different. So cosine 215 is negative 0.819. Sine of 215 is negative 0.57. And tangent well, let's see what sine divided by cosine is first. So if I take the answer and I divide it by negative 0.189, I get 0.7.
I thought it was
So I did
No,
sine
yeah.
divided by cosine, right? So I'm just checking that guess, that maybe it's sine divided by cosine. So if tan of 215 is 0.7, then that's probably a good guess. So let's try tan 215. Yeah, what a fantastic hypothesis. Turns out maybe is not needed. This is true. Sine divided by cosine is always tangent. Let's check if it works in radians. So sine of 5.3 is negative 0.83. Cosine 5.3 is 0.55. Now if I take my sine value, divided by my cos value, I'm hoping that my tangent is negative 1.5. Tan of 5.3. Yay! It works. So from the first page, sine of an angle is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So sine divided by cosine is opposite over hypotenuse divided by adjacent over hypotenuse. And if you divide two crazy fractions like that, you can multiply by the reciprocal. O over h divided by times h over a. And the h's cancel off, and you're left with opposite over adjacent, which is tangent. QED, quad erit demonstratum. That's what you write at the end of a proof. Latin for what needed to be proved has been proven. So, whenever you see an angle that doesn't have a degree sign beside it, that means that you want to be in radian mode. So cosine of negative 1.6 means cosine of negative 1.6 radians. So I can't do this in my head. Just plug it in. And you get negative 0.2029. To 4 decimal places. Is 292. Now, can you find 3 other angles that have the same cosine ratio? Okay, so adding 2 pi to the angle gives you a coterminal angle. So if I take cosine of 4.68, I also get the same answer, negative 0.0292. Because those are both in the same quadrant, they have the same terminal arm. So to find another angle that also has the same cosine, you could do 2 million pi's. Okay, if I do cosine of that angle, 628,31851, If I do cosine of that angle, I should get the same answer. Yep. I can add as many even numbers of pi as I want to, and the cosine will still be the same. So it repeats every 2 pi. Okay, so that one was like cosine of a whole bunch of pi's minus 1.6. Or you can be simple and do like negative 1.6 minus 2 pi. Which is negative 7.88. And cosine of that angle is also negative 0.0292. Okay, so when you see the degree sign, that means you need to change your calculator into degree mode and then determine the tangent. You get negative 0.3249. Oh, you need me back. So we want to find the next 3 larger angles that have the same tangent ratio. So how can you get another angle that has the same tangent? Add 360. So we want the next 3 this time. I don't let you guys have as much creativity with this one. I added a bracket on accident. There we go. So 522. Tangent of that angle is the same answer. But that's not the next biggest one. That's why I left some space. You can just add 180. Tangent special. Tangent repeats after every 180 degrees. So all you have to do is add 180 to the tangent, and you should get the same answer. If this doesn't work for sine and cosine, it's only for tangent. Tangent repeats every 180. So 10 of 342 should also give me the same ratio. So I can just take the previous angle and add 180. And you get the same answer. So 10 of 702 is also negative 0.3249. And that's because tangent repeats every 180 degrees. Now, multiple choice question. There will be a question similar to this on your test, and it's one that people seem to have trouble with every single year that I teach it. So see if you can just figure out what in the world are they asking for in this question. Are you able to draw a diagram that represents the situation? And then take your best guess to what the answer might be. So the point P is the point where the terminal arm intersects the circle. So we can draw a circle. Draw a circle. So that's the x squared plus y squared equals 1 is just a circle. And then I can draw any terminal arm. So my terminal arm is just a line from the origin out into space. My angle theta is the angle in standard position. And the point P is where those two things cross, where the circle and the terminal arm intersect. So it's right here. And that point is the point MN. So now if I draw a triangle there, then M is the length, N is the height, and because it's a unit circle, the radius is 1. So sine theta, opposite over hypotenuse, or N over 1. B. Okay, so your homework for today comes from page 221, number 5. And that's just the sine, cosine, and tangent ratios, not the secant, cosecant, and cotangent.